In this video, I'll be proving that Matt Parker's and Steve Mold's solutions for this hanging a portrait problem are actually the optimal solutions. So first of all, what is the hanging problem? First of all, what the hanging problem asks is, if you're given n hooks, let's say h1 all the way up until hn, and you're given the ability that around the ith hook for I equals 1 until n, around the ith hook, you can wrap around it clockwise, which I'll call xi, or you can wrap around it counterclockwise, which I'll call xi inverse. And the problem asks, what is the optimal solution for each of these ends to where, if you remove any one of these hi's, the rest of the hooks will untangle. Now what does this mean formally? Well, what this formally means, if you're given x1 to xn, and these are all elements of a group, and you're also given their inverses, x1 to xn inverses, so in this case, xi represents going clockwise, xi inverse represents going counterclockwise around the ith hook, then does there exist a formal multiplication of these elements? So let's go ahead and do an example where n is 3, such as x1, x2, x3, x2 inverse, x1, x3 inverse, to where if you remove all mentions of an xi, so let's remove all mentions of x2, that it will reduce to the identity element of that group. So what will we get out of here? Well, we'll get x1, x3, x1, x3 inverse. This doesn't work, like at all. Let's go ahead and do an example where it does work. And this is when n is 2. The solution is x1, x2, x1 inverse, x2 inverse. Why does this work? Well, let's go ahead and remove all instances of x1. We get x2, x2 inverse out of there, which reduces to the identity element. All right? Let's go ahead and alternatively remove all instances of x2. So we get rid of x2, get rid of x2 inverse. Well, then we'll have x1 and x1 inverse, which will go to 1. So n equals 2 is an example where it works. And let's go ahead and define this generally. Definition. It's going to be a definition of what I call an n solution. It's a formal product of all of these different 2n symbols. So you'll have x1, x2, x1 inverse, x2 inverse, x3, x4, whatever. You're multiplying that in some order. Let's call it L, such that removing all instances of xi and xi inverse for I equals 1 to n, and you just pick a specific I, such that removing all instances of that in that product will result in the identity, will result in 1. Now what I'm going to represent removing by xi and xi inverse, I'll represent this by L backslash xi. And by the definition of an n solution, L removing all instances of xi and xi inverse will have to be 1. And this is for all I equals 1 to n. And so that is the statement of the definition of an n solution. Alright, now if you're confused by this notation, let's go ahead and do an example. If I were to do x1, x2, x1 inverse, x3, and I were to remove x1 from this, this would result in removing x1 and removing x1 inverse from it, which will give you x2, x3. And so that's what that notation of the backslash means. Now, is this standard notation? I don't think it is, but it's the notation I'm going to use because I couldn't think of any better notation. Alright, let's go ahead and look at a very easy solution that arises from this. And it's going to be called the trivial solution. And the trivial solution is just 1. And this is for any n. Why is that the case? Well, let's go ahead and do 1 removing xi. And this is for any such xi. what will that result in? Well, 1 is just the identity element on its own. And so if you remove xi from it, there's no xi's in the element, and so you just get 1 out the other end. And that's true for any such i's, because none of those xi's are actually in it. You get the same element out the other end, which happens to be 1, which is the requirement for it being an n solution. Now, the solutions we're actually interested in are non-trivial solutions, ones that are not the trivial solution. And there's actually a theorem about these non-trivial solutions, and it says that all non-trivial solutions, all non-trivial n solutions, let's say L, must contain all xi's for I equals 1 to n. So what does this mean? Well, that means it must have at least one instance of xi or xi inverse in this solution L. Now, why is that? So let's go ahead and suppose that we didn't include either an xi or an xi inverse. Suppose L doesn't include, let's call it xi naught. So I naught is the index for the variable it does not include in the formal product. Well, then let's go ahead and look at L removing xi naught. Well, there's no xi naught in L, and so you just get L out the other side. But because this is an n solution, L removing xi naught must be 1, and so L is equal to 1. You can see by the transitive property here, you get that it's just the trivial solution, where the solution is just 1. And so all non-trivial n solutions must contain at least one of those xi's. And in addition to this, we can make that a little stronger, where there are the same number of xi's and xi inverses in L. Why is that the case? Well, it's the case because suppose we just had xi in L. Then, if I did L removing xj for j not equal to I, so we're removing some other element, what will I get out the other end? Well, I'll get out at least an xi, because there is no xi inverse to cancel it out. In order for this L removing xj to go entirely to 1, every single one of those xi's must have the corresponding inverse to go with it, because if you don't have that, well, then you're just going to have leftover xi's. And so there are the same number of xi's and xi inverses in L. Now, the reason why I'm not writing this as a theorem is because it's kind of a basic fact. All right, now let's go ahead and prove the part that I really wanted to get to. And it involves an operation called the commutator, which will do AB, A inverse, B inverse. So A commutate B is AB, A inverse, B inverse. So for instance, x2 commutate x3 would be x2, x3, x2 inverse, x3 inverse. And right now, let me get out an important fact. It's that if L is an n solution, that implies that L inverse is an n solution. Why is that? And what does L inverse even mean? Let's do an example so that you get a feel of why this is true. I'm not actually going to prove it, but it's very easy to prove. Let's do L equals x1 times x2 times x1 inverse times x2 inverse. You know that this is a solution. Let's go ahead and calculate what L inverse would be. Well, it would be x1 times x2 times x1 inverse times x2 inverse, and then all of that inversed. Well, how do I actually inverse all of that? I'll go ahead and show you how to do it. You flip the order and you do the inverse of everything inside of it. So we start with x2 inverse and we invert it, which goes to x2. Then we do x1 inverse, we invert it, which is x1. Then we do x2, we invert it, we get x2 inverse. We do x1, we invert it, we get x1 inverse. All right, how do I know that this is correct? Well, we would want L times L inverse to be equal to 1. Let's go ahead and calculate that. L is
x1 times x2 times x1 inverse times x2.
Inverse. We multiply that by the inverted one.
x2 times x1 times x2 inverse times x1 inverse.
X2 inverse, x2 cancel each other out. What are we left with? We're left with x1 times x2 times x1 inverse times x1 times x2 inverse times x1 inverse. Those two just go away. You can see right in the middle we have an x1 inverse times x1, which leaves x1 times x2 times x2 inverse times x1 inverse. Those go away. We get x1 times x1 inverse. Those go away. And so that's how you get L inverse. Now, how do I know that this is also a solution? That L inverse is also a solution? Well, let's go ahead and check. Let's do L inverse removing x2. Well, L inverse removing x2, well, we skip over that first x2, we do an x1, x2 inverse we skip over, we do an x1 inverse, and x1 times x1 inverse is just going to be 1. And so you can see that that works out, and you can also prove it for removing x1 from it. So now you can probably tell how you would do the general form of this. So let's just write this out as a statement right there. All right, I'm not going to explicitly mention it like the first theorem. Okay, let's go ahead and prove the theorem that I've been building up to. It is that if L is an n solution, so we have this n solution, the smallest n plus 1 solution of the form L times A, where L is this n solution, A is going to be some more stuff added on, is the commutator of L with xn plus 1. And writing that out explicitly, it's going to be L times xn plus 1 times L inverse times xn plus 1 inverse, straight from the definition of commutator. So let's go ahead and write out L times A in a really general form. And the form I'm going to write it out in is L times A1 times xn plus 1 times A2 times xn plus 1 inverse times A3 times, you get the idea, it'll go up until A2k. It has to be even because the same number of xn plus 1 and xn plus 1 inverse times xn plus 1 inverse, and then times 2k plus 1. Now, this is arbitrary the way I did it. Any one of these xn plus 1s and xn plus 1 inverses could be swapped and you'd still have a solution, but those are all equivalent solutions. And so we don't need to worry about that. And the requirement I'll make is that each one of these AIs does not include xn plus 1 or xn plus 1 inverse. So that means that we have L, a bunch of stuff that only includes x1 to xn, times xn plus 1, times a bunch of stuff that only includes x1 to xn, times xn plus 1 inverse. So we basically separate it out into L, and then all of these individual components which do not include xn plus 1, and we separate them by xn plus 1s and xn plus 1 inverses. So this way, we just break it up so that we see where each individual xn plus 1 or xn plus 1 inverse is in this sequence of multiplication, and all of these just represent all of the symbols in between them. So here is a fact. Each AI is an n solution. Why is that the case? Well, let's go ahead and do L times A, removing xi, and this is for I equals 1 to n. So this way it is not xn plus 1. What is this going to give us? Well, it's going to give us, we know that L is an n solution by the hypothesis of the theorem. And so that part will go to 1. Alright, then we'll have A1 removing xi times xn plus 1 times A2 removing xi times xn plus 1 inverse, all the way up until a2k, removing xi, times xn plus 1 inverse, times a2k plus 1, removing xi. Alright, sorry I ran out of room there. What is required for this to actually reduce to 1? Because we want this to be a solution. What is required for this to go to a 1? Well, the only way for this to go to a 1 is for each of these xn plus 1 and xn plus 1 inverses to meet up with each other. Well, how do I do that? Well, the only way is to get rid of these. And note that none of these include xn plus 1 or xn plus 1 inverse, so they could not possibly cancel out with one of these, or some trick to be done where these could make these cancel out, because it's formal sums in a specific order. You have to keep it in this order. There's no commutativeness. There's no commutativity. So what you require is that every single one of these goes to 1. Because if they didn't, you would actually just be left with tons of excess symbols, and these ones would never cancel out with each other. Unless these go to 1s, and because it's a solution, they have to go to 1 in order for all of these to cancel out with each other. So what that tells you is that ai, removing xi, for I equals 1 to n, is going to be 1. Which means, by definition, that ai removing xi is equal to 1, which means, by definition, ai is an n solution. Because remember, it's true for I equals 1 to n. Now I'm going to erase that proof, because we're done with it. And we're just going to use this statement now, that each ai is an n solution. Now I also want you to acknowledge that if I do L times A, removing xn plus 1, what do I get? Well, L stays the same because it doesn't have an xn plus 1. Then we get A1. We remove that, so it goes to A2. We remove that, so it goes to A3, all the way up until A2k plus 1. This is the final little bit that does not include n plus 1. And because we're removing xn plus 1, these are unaffected. Just every single one of these xn plus 1s between them get removed. And by the fact this is a n plus 1 solution, we know that this must go to 1. Alright, I'm going to use this later on. And what I mean by later on is right now. I'm going to show that given this solution, you can reduce it. You can reduce it to S is equal to L times A1 times xn plus 1 times A2 times xn plus 1 inverse times A3 times A4 all the way up until A2k plus 1. No extra xn plus 1s. This is getting rid of, this is gotten rid of. All of those are gone. How do I know that this is still a solution? Well, let's go ahead and check. What is S removing xi for I equals 1 to n? Well, by the same logic before, it's going to be equal to L goes to 1. Every single one of these is an n solution. And so they all go to 1 as well. So A1 goes to 1, xn plus 1, unchanged. A2 goes to 1, xn plus 1 inverse, unchanged. A3 goes to 1, A4 goes to 1, A2k plus 1 goes to 1. And you can see we're just left with an xn plus 1 times xn plus 1 inverse. Those go away, and we're left with a 1. Great. Now let's go ahead and do the final one we have to check, which is S removing xn plus 1. What is this going to be equal to? Well, it's going to be equal to L times A1, remove that, times A2, remove that, times A3, times A4, all the way up until A2k plus 1. And you can see that this is the exact same product as L times A, removing xn plus 1. And by the fact that this is a solution, we get that it's equal to 1. And so we get that this S, removing xn plus 1, is still 1 out the other end. And so that proves that this reduced S, which just got rid of those excess xn plus 1s and made it smaller, is still a valid solution. And so what we should be looking at is we shouldn't even acknowledge each of these as their own separate symbol. We should just acknowledge this as a single symbol, C, because this is just the product of things without xn plus 1 in it. So we can just reduce that to a single symbol, C. All right, let's go ahead and write out this S right up here at the top, this reduced form for L times A. So now, using that fact, I'm going to simplify it into a form where, of course, L is going to be out front. We're going to replace A1 with A. We're going to multiply that by xn plus 1. The A2 before is now going to be a B. Multiply that by xn plus 1 inverse. And the product trailing off at the end is now going to be a C. So now this looks a lot simpler. And of course, this solution will work whether or not you swap the xn plus 1 with its inverse or not. The order is completely arbitrary here. Now this is a lot simpler than what we had before, but it's not the simplest form I can put it in, because, well, let's go ahead and first acknowledge that S removing xn plus 1 is going to be equal to, well, L stays the same, A stays the same, that goes away, B, that goes away, times C. So it's L times A times B times C. Now we can actually reduce this even further to a solution I'll call S prime, which is going to be equal to L times xn plus 1 times A times B times C times xn plus 1 inverse. So let's go ahead and check if this is a solution. We remove xi, what will we get? L goes to 1, you have an xn plus 1. Each one of those are n solutions, so those go to 1, and we get an xn plus 1 inverse out the other end. They cancel each other out, we get 1. If we do S prime removing xn plus 1, we get L. That stays the same. We remove that, we get A times B times C, which all stay the same, and we remove that. Oh, look at that. This is the same product as S removing xn plus 1, which is 1. And so this is an n plus 1 solution as well. And the reason why I wrote it like this is because, well, notice that this will either remain the same size, where A times B times C will just remain the same, or it will reduce in size, where some elements of A will cancel out with elements of B, and some elements of B cancel out with elements of C. And so this will either stay the same or be reduced in size. And what I can now write this as is a general form. S prime is equal to L times xn plus 1 times D times xn plus 1 inverse for the general solution. What does this tell me? Well, it tells me that S prime removing xn plus 1 is equal to L times D has to be equal to 1. What does that mean? Well, it means that D is L inverse. That is the only element which will invert L to 1. That is just by the fact that you can multiply both sides by L inverse. So you get D equals L inverse, meaning that the general smallest solution is going to be L times xn plus 1 times L inverse times xn plus 1 inverse, and you can swap those two. And you can swap the xn plus 1 and its inverse, which is equal to the commutator of L and xn plus 1. And that's QED. Now the final thing I'm going to prove is that the optimal n plus 1 solution will start with the optimal n solution. And I'm using the, I really mean A, because it can be any of the possible optimal solutions. So any optimal n plus 1 solution will start with an optimal n solution. Why is that? Well, suppose we have an optimal n plus 1 solution, L n plus 1. Well, this is going to be equal to A times xn plus 1 times B times xn plus 1 inverse times C. Now, the reason why I'm just writing it like this and not adding on anything else is because of the same logic I used here. You could reduce it to this form if it's optimal. Now, what can we tell about this? Well, let's go ahead and do Ln plus 1 let's go ahead and do that, removing xi. Same logic, this is equal to a removing xi times xn plus 1 times b removing xi times xn plus 1 inverse times c removing xi. And you can see the only way for this to reduce to 1 is for each and every one of these to go to 1. And so what you get is that A, B, and C are n solutions. So each one of those is an n solution. What else do we get? Well, we get that Ln plus 1 removing xn plus 1. What's that going to be equal to? Well, I think you can see by now, it's A times B times C, and that has to be equal to 1. Now, something I can do is set A or C to the trivial solution. Why is that? Well, because that will reduce the length, it'll reduce the amount you have, and it will remain an n plus 1 solution. Now, why can't I do the same with B? Well, let's say we removed B and we made it the trivial solution. Well, then I would have A times xn plus 1 times 1 times xn plus 1 inverse times C. Those cancel out, and we just have A times C, which, I don't know if you know that, neither A or C has an xn plus 1 in it. By theorem 1, that means that the solution that we got was the trivial solution, and that's not what we wanted. Neither of these A times C has one of those xn plus 1 or xn plus 1 inverses, does not obey the hypothesis here, therefore it is a trivial solution, which is not what we want from the optimal solution. We want one where everything is hooked. So that tells us that we can't get rid of B, but we can get rid of A or C to make this optimal. So I'll just go ahead and choose C for simplicity, but you could technically choose A to get rid of. And we get Ln plus 1 is equal to A times xn plus 1 times B times xn plus 1 inverse. And I think you can see where this is going. If you remove xn plus 1 from here, you get A times B, which has to be equal to 1, which means B is A inverse, which means we'll have Ln plus 1 is equal to A times xn plus 1 times A inverse times xn plus 1 inverse. In order for this to be optimal, A has to be an n solution, so that means that A is an optimal n solution. So in finale, we have it in the form where it starts with an n solution times xn plus 1 times A inverse times xn plus 1 inverse, which would have just been a follow-up of this first theorem, but I also wanted to do the first theorem on its own. So I'm going to erase this side of the board, and I'm going to use those two facts to figure out the optimal solutions for every single one. Alright, what is the optimal 1 solution? The optimal 1 solution is just going to be x1. Because that is a length of 1, it's the only solution you can have that is of length 1, because there's only one symbol, and the only other solution would be 1. And so we ignore the trivial one, we get x1. Alright, what is the optimal 2 solution? Well, let's go ahead and look at this theorem, which says an optimal n plus 1 solution will start with an optimal n solution. So that means it will start with x1. And what it says is that the optimal n plus 1 solution, where it begins with the solution, is the commutator of that solution with xn plus 1. And so the solution we get out the other end is x1 commutated with x2, which is x1 times x2 times x1 inverse times x2 inverse. And then the 3 solution, well, using this theorem and this theorem combined again, if I call this S2, the optimal 2 solution, I call that one S1, the optimal 1 solution, the optimal 3 solution is going to be S2 commutated with x2. Sorry, x3, because it's a 3 solution, that's the n plus 1 there. Alright? Which is then going to be equal to S2, x3, S2 inverse, x3 inverse. You get the idea. So what this would actually end up being
is x1, x2, x1 inverse, x2 inverse, x3. Then we flip it and do the inverse of everything. And we multiply by x3 inverse.
And so that's the optimal 3 solution, which is actually Matt Parker's solution and Steve Mould's solution. It's equivalent to both of them. Alright, now you could continue this on to the 4 solution, where this 3 solution, you just commutate with x4, and that will be the optimal 4 solution. In general, the optimal n plus 1 solution is going to be, well, Sn plus 1 is going to be equal to the commutator of Sn with Xn plus 1. And that is the inductive definition of the optimal solution, and therefore Matt Parker and Steve Mould were optimal in their solutions of the hanging portrait problem. Oh my god, please like or something, or subscribe or whatever. I did that all, and it's hurting my voice. I recorded this twice. Anyway, that's it.